Ever notice how a pizza box is a circle for a circular pizza, but then you get those triangle slices? It's all about shapes, right?
Yeah.
And how we measure them. That's what today's deep dive is all about. Mensuration. Unlocking the secrets of shapes. From everyday stuff to those crazy, intricate designs you see everywhere, like in buildings and nature. But don't worry, we're not cracking open a textbook here. We're going to make it fun, with real-life examples and hopefully a few aha moments along the way.
It's funny, though, isn't it? We use these concepts every single day without even realizing it.
Oh, totally.
Like packing a suitcase.
Packing a suitcase, yeah.
Trying to arrange furniture. Heck, even just figuring out how much wrapping paper you'll need for a present.
Yeah.
That's all mensuration in action.
It really is. Okay, so our sources kick things off with a shape we all know, the rectangle. Picture a park, like the one you probably hung out in as a kid, that perfect rectangle, maybe 30 meters long and 20 meters wide.
Okay, so imagine you're walking around that park, right? The total distance you cover all the way around, that's the perimeter. In this case, a nice leisurely 100 meters.
Easy peasy.
But then there's the space inside the park itself, where you might have had picnics, tossed a frisbee around. That's the area. And for a rectangle, it's just length times width. So in our park here, that'd be 600 square meters.
See, so far so good. But it gets way more interesting when we ditch the basic rectangle. We've got squares, triangles, parallelograms, and of course, the always important circle.
Ah, the circle pops up everywhere in nature, design. And you're right, each shape has its own set of formulas, kind of like its own secret code to help us understand it. Like the area of a circle that's where R is the radius, so the distance from the center of the circle to the edge.
Right.
Or the circumference. Think of it like the perimeter of our circle, that's 2R.
It's like having a cheat sheet for understanding the world of shapes, which I am here for. Now, one of our sources uses a really cool example to explain trapeziums. Imagine a plot of land, but it's not a perfect rectangle. It's got this unique shape with one pair of parallel sides. That's our trapezium.
And what's cool is that we can break this odd shape down into ones we already know. Picture drawing a line across the top, essentially chopping up that trapezium into a rectangle and a right-angled triangle.
Oh, I see where you're going with this.
Exactly. We can calculate their area separately, add them up. And this actually gives us a super handy formula. The area of a trapezium is just half the sum of its parallel sides, multiplied by the perpendicular distance between those sides.
So we're basically giving that weird-shaped plot of land a geometry makeover. But seriously, trapeziums are way cooler than I thought. Speaking of cool shapes, our sources mention this triangulation thing. What's that all about?
Okay, imagine, right, you've got a slice of pizza, but it's not a normal triangle slice. It's quadrilateral. Could be a square, could be a rectangle, could be totally wonky. Doesn't matter. Now, you slice that pizza diagonally. What do you have?
2 triangles.
Exactly. And we know how to find the area of a triangle, right? So we just calculate the area of each of those pizza slices, add them together, and boom, we've got the area of the whole quadrilateral.
Okay, so triangulation is like the pizza slicing secret weapon of geometry. Love it. But what about when we're dealing with more sides? Like pentagons, hexagons, all those polygons, they seem kind of scary.
Polygons do sound kind of intimidating, but the same ideas still work. Take a pentagon, for example, our 5-sided friend. Our sources talk about how you can divide it up into, you guessed it, triangles. You just got to figure out how to slice it up.
Right.
Calculate the area of each triangle, add them all up, and you've cracked the code of the pentagon's area.
So whether it's 4 sides, 5 sides, heck, even a dodecagon with its 12 sides, we can just keep making triangles. It's like having a geometry toolkit. This makes me wonder, though, where do we actually use this polygon stuff in real life? Besides perfectly sliced pizza, of course.
Well, think about it. Architecture, design, they're full of polygons. Parks, buildings, even those super intricate tile patterns you see in mosaics. They often use these geometric shapes. Like, imagine a park designed as a pentagon. Knowing how to calculate its area could help figure out how much grass seed you need, how many benches would fit, practical stuff.
Wow, that's so cool. I'm looking at the world in a whole new way now. But we've been stuck in, flatland this whole time, dealing with just 2 dimensions. Our world is 3D. How do we even begin to measure something like a box or, say, a can of soda?
That's where we move from area to the world of volume. It's like upgrading from a flat map to like a 3D model of the world. Think about your bedroom. It's got length, width, but then also height, that 3rd dimension. That's where cubes, cuboids, and cylinders come in.
Right. Cubes, where all the sides are the same, like those fancy ice cubes you sometimes see. Then there's cuboids, like a shoebox, with those rectangular faces. And of course, cylinders, our good friend, the soda can, with those circular bases.
And just like our 2D shapes, these 3D shapes have formulas to unlock their secrets. But before we jump into the volume itself, let's imagine we're painting one of these 3D shapes. The amount of paint we need that's related to its surface area, basically the total area of all its faces.
So if we were wrapping a gift, for instance, we'd need to know the surface area to make sure we had enough wrapping paper.
Exactly. And it's the same idea for cylinders. Imagine slicing open a soda can and laying it flat, unrolling it. You'd have the two circular bases and then a rectangle that wraps around the can.
Oh, like a label?
Yeah, exactly. So by calculating the areas of those shapes, we can figure out the total surface area of the whole cylinder.
Okay, I'm starting to see how this all connects. It's like we're deconstructing these 3D shapes into their 2D parts to understand them. Kind of like what we did with the trapezium, actually.
You got it. And this whole surface area thing, it's got real-world uses, too. Imagine you're designing, the packaging for a new product. You'd want to use the least amount of material possible, right? But it still needs to fit your product inside.
Right, you don't want to waste cardboard.
Exactly. Or think about designing a building. You'd use surface area to figure out how much material you'd need for the walls, floors, roof, the whole shebang.
It's like geometry is secretly behind so many things we just don't even think about. But now I'm really curious about this volume thing.
Well, volume is all about how much space something takes up. It's about how much stuff we can fit inside something, like how much soda can fit in a can or how much stuff you can cram into that shoebox.
So it's kind of like we're talking about the difference between measuring the size of the gift box itself versus how many actual gifts you can cram inside.
Perfect way to put it. And just like with area, we've got specific formulas for figuring out volume. For a cuboid, remember our trusty shoebox? It's just length times width times height.
Which makes sense, right? Because we're basically figuring out the space taken up in all 3 dimensions.
Exactly.
And since a cube is just like a special cuboid where all sides are equal, its volume's just the side length cubed. But what about cylinders? Those curvy sides always kind of mess me up.
They're not as tricky as they seem. Remember we were picturing a cylinder? Like a stack of circles?
Yeah.
So all we got to do is calculate the area of one of those circles, good old SARP, and then just multiply it by the height of that whole stack, which is the same as the cylinder's height.
Like building a tower of coins, basically.
Exactly.
The area of one coin times the height of the tower equals how much space your coin tower takes up. I'm starting to see the pattern here. No matter what shape we're looking at, there's a way to, break it down and figure out its volume.
You got it. And our sources really emphasize how crucial these volume calculations are in everyday life. Think about packing a moving truck. You're essentially solving a volume puzzle,
Yeah,
right?
sure. Trying to cram all those different size boxes in.
Right. It's all about figuring out how to fit everything in that limited space.
Or even designing something like a fish tank. You don't want to put your poor fish in a tank that's too small for them.
Exactly. You need to calculate that volume carefully to make sure they've got enough space to swim around comfortably.
It's really amazing how this stuff pops up everywhere.
It really does.
Yeah.
It shows just how intertwined math is with our everyday lives, even if we don't always realize it.
Totally. This deep dive has completely changed how I see the world, honestly. But before we go, our sources left us with a pretty thought-provoking question.
Oh.
What happens to a cube's surface area and volume if you, double the length of its edges?
Ooh, that's a good one. It's not just about plugging numbers into a formula anymore. It's about really getting that relationship between shape, size, and scale.
So it's about seeing how changing one thing about a shape can totally change its other properties.
Exactly. And that's what I love about mensuration. It's like a key to unlocking a deeper understanding of all these geometric principles that shape our world.
Like we've got this secret decoder ring for the universe now. Well, that about wraps up our deep dive into the world of mensuration. Hopefully, you're all looking at boxes, buildings, even your morning coffee mug a little differently. Until next time, keep those brains buzzing.